All right, let's get started. So, a couple of reminders. Of course, midterm corrections, let's get those in. How's your class today? And then, of course, don't forget about your paper. That's kind of on the back burner, hopefully. So, paper. So, due at the end. And again, right, this is just a draft, so 3 pages. If you want to show me an outline or anything before, I'm more than happy to help or meet with y'all, set up an appointment. So get that taken care of. And then I should have kind of reconciled the grade book, at least with like quizzes that have been missing. So if that was you, double check that all your grades are correct. I still have to catch up on like the paper grading, so I'll work on that though. And then don't forget about the talk this Friday for extra credit that Tony Cremo set up. There was a flyer around here. But I believe it is Friday at 4 p.m. and it's going to be in 132 HEC, so the big lecture hall. And I think there'll be snacks and drinks again. It's generally what they've been doing. And again, I'll give 5 points of bonus. And I'll also make sure that it's recorded in some fashion. I don't know if it'll be on my YouTube, but I'll still be helping record it, so it'll be somewhere. So we'll get that link up. All right, so now we're going to start going into kind of chapter 18. And so kind of the key with chapter 18 is, right, so we still need chapter 17. So obviously that was kind of our rate laws, our fundamentals. And then we're just kind of going to be building upon this rate law. And then, okay, based upon our rate laws, right, again, we have to determine this experimentally. So again, you'll notice the type of problems, right? There has to be a lot of data, blah, blah, blah. But basically we're saying, okay, once we derive our rate law experimentally, what does that mean then for our mechanism? What does that kind of imply? And so, you know, kind of teasing out the reaction mechanism is, again, a lot easier said than done. I was trying to pull up some papers, not having good luck. Just trying to show some mechanistic studies. I'll try to pull up some examples as we go along. And so, okay, let's just kind of put ourselves in the right frame of mind, and then what are we looking at? So, of course, right, we have our chemical reactions, and they're generally described, right, with our reactant molecules and our product molecules. And then so kind of the next thing that we have to think about, right, is, again, how do actually molecular collisions occur? Because, right, they have to meet, they have to be at a correct orientation, and then also have the proper activation energy. And so then it brings up this statement. So we have, okay, well, the probability of more than 3 molecules colliding at the same instant with the proper orientation and sufficient energy is negligible. And so all this is saying is, right, when we're looking at our individual reaction mechanisms and what's going on, right, it's probably always going to be 2 things colliding, right? Because, again, 3 things at the correct orientation, that's probably not likely. And of course, right, again, from our rate law, we're not saying that we can't have all these things involved, just it's not necessarily happening at the same time. And okay, well, what's the implication, right, of this statement? Okay, well, so then again, we're saying that these reactions occur in a series of small reactions. So either potentially just one, right, maybe there's a dissociation or some sort of orientation that has to happen, or, you know, maybe 2 molecules. And it does mention, again, maybe 3, but not likely. And so then we're going to be looking at, of course, how to describe our reaction mechanism. So we'll be getting into that. And again, right, it'll be still related to the rate law. And so again, it emphasizes, right, so knowing the rate law then helps us kind of understand these reactions. And again, we'll see how that unfolds. But all this is still to say, right, that we need experimental data. So we can't just look at a problem and conjure up, right, what's going to happen. We have to look at a reaction, we have to have data, we have to have rates to get it. All right, so here's some examples here of what we're getting at. And so, right, we're just kind of given this overall reaction. So you could obviously be given that on a test. So we're looking at this reaction of hydrogen plus iodo-chloride gives us HCl plus iodine. And then, right, what's not clear from this is the mechanism. So, right, you would have to determine this mechanism experimentally. And so now we're saying, okay, well, if we actually were to understand the mechanism, so what we want to do is, so these reactions are elementary step. So now they cannot be broken down into simpler steps. And so these are what's actually interacting, right? So now we're saying this is what's actually happening step by step. So again, right, this is just our overall reaction, what we might observe. But then really the question too with kind of maybe figuring out this mechanism is, you know, how do you quantify HI, maybe detect that and notice what this is. So this is going to be an intermediate. So, right, a species that is present in the middle of the reaction, then it goes away by the end there. And so kind of being able to track those intermediates, that helps us give insight into the mechanism. And then again, we can kind of break down this mechanism of what's going on. So the first step is just H2 reacting with one equivalent of our iodochloride, and then we make one equivalent of HCl, and then our equivalent of our intermediate, and then our intermediate, right, goes on to do another step, so another equivalent of iodochloride, giving us our second equivalent of HCl, and then finally, right, our final product of iodine. And so, okay, like we said, we labeled our intermediates. So it's a product in step 1, reactant in step 2, and then overall consumed. So it does not show up right in the overall reaction there. And so again, definition, intermediate. And so again, we're going to be looking at these little steps and classifying them. And so we'll determine whether a step is unimolecular, so that just means involving one particle. Bimolecular involves two particles, so it could be, right, the same particle just reacting. So, right, this is basically like A going to B. This would be A plus A, right, gives us something. Particles, even again, if it's three of the same, somehow going in some way to make one thing. And again, right, we'll put not likely. It's still there. And so then kind of the point is, so each step in these mechanisms, it's like its own little reaction and activation energy and own rate law. And of course, again, right, will equal overall though. So just kind of keep that in mind, right? So it's like, again, we're going to be looking at our rate law of each individual step, but then we're going to figure out, again, how to relate that to our overall rate law that we looked at. And then, right, we'll be able to figure out from our molecularity, right, and from our steps and our rate law, then we'll be able to verify our overall rate law. And so again, right, it's telling us we have to determine it experimentally, very important. But again, right, each step of our equation will help us kind of deduce our rate law here. All right, so all that's done up here now is we're just kind of rewriting, right, our rate based upon our equations from chapter 17. And you might want to pull up, right, your chapter 17 cheat sheets. I forgot to update the live notes for 18. So I'll do that shortly. But again, right, we're just expressing our rates or just writing this sort of expression initially, right? And so that's all that's happening now in 18, or in chapter 18, and then this example here. And so let's just kind of break down, right, what's been done here. So now we can write out, right, again, each kind of individual rate law for each step. And again, right from our mechanism, so now we can kind of break it down. So we're saying, okay, well, step one, and again, that's all, I'm just rewriting what's shown here. So in our step one here, again, some rate is just going to equal to whatever constant, right? We don't have any numbers. We're just, again, writing this out. And then two things are, right, one equivalent coming together, so H2, and then one equivalent of our iota chloride. And so that just gives us, right, our very general rate there. And then, right, obviously step one, K1, and then again, step two, that's all that we're drawing here, that we have some sort of rate. It's going to be equal to K2, whatever K2 is for step two. And then now looking, again, from our equation, right, so we have HI. So this is where we'll do a little math later. But, right, it's an intermediate. Again, so we're just emphasizing that this HI is not a part of our original rate law expression, right? So if we were to look at this, we don't have our rate law expression yet. We could kind of write what we expect, since we're going to be losing, right, this at 2 times the rate. But notice that HI is not in this direct expression, right? Again, we'll rearrange this mathematically, but we just kind of see that for this step. Okay, so now we have our intermediate HI, again, reacting with our one equivalent of iota chloride. So that's all that's done so far. And okay, so this next chart is again to just kind of show the rate law for these elementary steps, how it should translate. So again, if it's just unimolecular, it's going to be dependent on that element A. If it's 2 of those, right, like we mentioned, A and A coming together, then that would translate to A squared again for that step. And, right, because that's the same thing as K times A times A. If they're different, right, it just means it depends on both those concentrations. And then obviously, right, all these 3 are rare, but at least you're aware of them. All right, so that's, again, we're just kind of laying out our mathematical framework. And so let's, again, figure out where this is going. Oh, sorry, question. To here or the chart, sorry? Okay, I'll show the chart for a second. So do we have the chart copied? And then we have this kind of just copied at least, or I'll try to, let me get this notebook going. All right, I'll post the link shortly. All right, so now we're here. And okay, so now we're starting to build up to, again, kind of the point of this and where we're going. And so now the next step is, well, usually there's some sort of what's called rate determining step or the slow step of our mechanism. And so in most mechanisms, there's one step that occurs slower. And so again, that's usually our rate limiting step. And so the effect is, of course, right, our product production cannot occur any faster than the slowest step. So again, this step will determine the rate of our overall reaction. And usually this is related to activation energy. So if it's a slow step, right, it has a large activation energy. There's where we could think about some sort of catalyst, right, to lower it, but that's not what this is necessarily about, right? We're just saying, okay, we have a step, high activation energy, right? That's our limit there. And then we have our cute little visual, so obviously a little traffic jam. And so, right, these 3 lanes don't matter. They're all limited by our merger here. And so that's, again, where we're going slowly, right, is we're trying to figure out what's our rate limiting step, and then how does that, again, correspond to our overall rate law. All right, so now we're starting to slowly get into the details and understanding where we're going with all this. And so now we have our reaction. So nitrogen dioxide plus carbon monoxide gives us nitrogen monoxide plus carbon dioxide. And then, so right, this is our rate law observed. So again, right, chapter 17 stuff now. Okay, this is what we observe from our reaction. Obviously determined experimentally. So right, at some point, someone saw some data and got this, right? They didn't just pull it out of thin air. Okay, so then, after we get this data, right, so again, the next step with chapter 18, where we're trying to take 17, is how do we take this rate law and turn it into kind of a mechanism of what's going on. And so kind of the thought, too, not that you would necessarily be kind of deriving this mechanism cold, but where it kind of comes from is, right, we have this NO2 squared. And so that's probably telling us at some point, right, NO2 and NO2 are going to have to react with one another, right? So they're going to be dependent. So again, just kind of thinking back to what we were saying here. So, okay, we have NO2 plus NO2, right? It has to react, giving us this sort of rate law. And so, again, that's what's proposed now for our mechanism, is that, okay, the first step of our reaction involves 2 equivalents of NO2 reacting to give us our intermediate of NO3, yeah. Sorry, repeat your question.
Yeah, that part. That's not the rate for the KN, not 2 squared, is it?
So, right, it's the rate for this reaction, but what we're noticing and what you're kind of seeing is, right, so this is no effect on the rate, right? Is that what you're kind of noticing?
It only has one NO2 like reacting, it's not A plus A.
Right, but so think back to chapter 17 for a second, because we don't have the data for this, right? So we're just saying at some point it was determined that it's second order with NO2, remember? what that means, and then it must be zero order with CO.
Okay.
But, right, we wouldn't be able to tell that from this equation.
Information and you're supposed to catch
Yeah, so right, that's why it's saying the rate observed, and I just kind of put this experimentally, because like we weren't given this direct data for how they got this. They're just saying, okay, now starting here, and then, right, good, because you want to recognize what it means, because you want to say, okay, yeah, my reaction is showing NO2 plus CO, but then our rate law is saying, well, it's not dependent on the CO, and it is second order with NO2. And so because it's second order with NO2, that's what leads to this kind of first step here of this proposal of like, okay, well, we have to have NO2 plus NO2 reacting. That's the first step. And then notice how they put slow here. So we're not, if you're not quite there, that's fine. We're going to tease this out. But right, they're already kind of teasing that this has to be our rate limiting step because this matches our rate law, right? So this is now our rate expression for just this first step, right? So now that we've just rewritten, so our rate of this reaction is equal to K1 for step 1. And again, from our mechanism, it's going to be NO2 squared. Does that make sense? And that's for everybody too, because this stuff can be a little tricky, right? Because like you have to depend on the data, you have to have data to determine this, and then now we're trying to take that data, right, a little step further of like, well, what is really happening? And that's what this mechanism is attempting to answer. And so again, because this is the rate law that we observed, the implication is this is our rate determining step. And right, maybe we need to put rate determining. And so then kind of with our proposed mechanism here, it says, okay, well then nitrogen trioxide goes on to react with one equivalent of CO, right? And that rate would be given, again, just what we would expect, right? Rate is equal to K2 times our intermediate times CO. But it's saying it's probably fast, right? Because this is not in our observed rate law. So not part of observed law, right? So that just means it's fast, right? It's not dependent on the concentration of either one of those, right? Because again, this step is our limiting one, so it's really dependent upon our NO2 concentration. And so again, right, this one was a little simpler in some senses in that we were able to, right, just verify that the rate law of the first step is the same as the rate law of the overall reaction. So again, right, this is saying that it is dependent upon NO2 reacting with itself first, and that is our limiting factor. Does that make sense to everybody? All right, so then, right, that's basically what Chapter 18 is leading us towards, right? Is again trying to validate these mechanisms. Is the mechanism that we proposed, does that match with the rate law? And so right here, it walks us through our conditions. So obviously, right, the elementary steps must sum to the overall balanced reaction. I mean, yes, obviously, to me that makes sense. But then, right, this is the key point that we really want to dig into is that our rate law that was predicted, right, by our mechanism. So once we break down the mechanism, it has to be consistent with our experimental rate law. So that's the key, and that's what we're digging into now with Chapter 18. And okay, so now we'll get into a little bit more mathiness. And so now the next question is, so right, we looked at this first mechanism. And of course, our first step was our rate limiting step. And so now we want to look at mechanisms with a fast initial step. And so of course, when you have a fast initial step, like we saw, then, or like we haven't seen it yet, but just in theory. So then that means our rate determining step may contain intermediates, which, right, is not a big deal, but we just have to kind of rewrite this and re-express it, right, in terms of our starting materials, which we'll work towards that together. And so it kind of gives us a hint of how we're going to accomplish that. But again, we'll go through the math together. But kind of the idea is, so if the previous step is rapid and reaches equilibrium, so now we have to, again, remember what equilibrium means. So the forward and reverse reaction rates are equal. So again, the overall concentrations would remain unchanged. And again, our product is our intermediate. And so, right, we'll see how we can substitute our equation and produce our rate law in terms of our reactants. So again, we'll walk through that. All right, so here is our setup here. So we're looking at this reaction. And so now we have, let's look at our overall reaction. So 2 equivalents of hydrogen plus 2 equivalents of nitrogen monoxide give us water and nitrogen. And again, right, data had to have been used, so we just accept it at this point that this was the rate law observed. So it's first order with H2 and second order with NO. And so then all that we want to do, so before I scroll down, so right, this would kind of be your problem of how it starts potentially. It might tell you, right, we have our fast step, this is our slow rate, and then fast again. And so all we want to do is now write and express our rate laws. And so let's do that. And so things to keep in mind, so again, right, equilibrium. So the forward and reverse reactions, the rate is the same. And okay, so let's go through what conclusions we have. So again, step 1, rate forward equals rate reverse. And so that's all that they are showing with this first step. And so, right, again, all we've done is kind of broken this down. So, right, it shows us the first step is 2 equivalents of NO reacting. So now we have, again, first step, we're just calling K1, whatever our rate constant is, times NO squared is equal to, and just set the reverse reaction to be, right, negative K, so K negative 1. And so that's going to be equal to, right, the consumption of N2O2, right? So this is your first expression. And so notice, again, what we're trying to do here. So we have our dinitrogen dioxide here. So again, this is our intermediate. So we can't just use the intermediate, right, in our rate law expression. And so that's all that we're trying to do down here, right, is substitute this new expression in for N2O2. And so all they've done, right, is take K1 divided by our rate. And it really doesn't matter, right, so, because we haven't solved for anything. So this is still just K in the end. We'll fix that at the end. All right, is that clear for this, just this first little part, what's happened. I just don't want to lose anybody because it's super mathy. All right, so now we just, again, right, we just wanted to set our intermediate equal to something in our reactant expression, okay? And then now we've done the same thing for step 2 here as shown. So again, you'd be given, right, this mechanism. So it says step 2 of this reaction is our H2 plus our N2O2 intermediate, right? And so it tells us slow rate. And so again, just writing it generically. So whatever our K2 is times our concentration of H2 times our concentration of our intermediate. All right, so that is what's shown and rewritten here. And so now I'll kind of work along the math so we can kind of see what they've done. But all they've done here, right, to get from here to here, is they've substituted this in. So let's just, so substitute expression for our intermediate, right? Again, we can't use N2O2 in our expression. It's not our reactant. And, right, again, slow step rate determining, so that's why we care to plug it into here, right? So this is our slow step. They told us that, right? Rate determining. But again, we want to express this in terms of reactants. So that's all we're going to do now is substitute, right, this in for there. So that's all they've done. So I'll just rewrite it as well. So again, right, our rate for step 2 is just K2 times H2 times our intermediate. Since we can't express it as the intermediate, go ahead and plug it into our expression. So that's where we get our NO squared then. And then, right, K1 over K negative 1. But again, all this can just simplify right to K. So now, right, same thing. That's where we got that. And again, we'll just simplify to K. And so, yes, right, this matches our rate observed now. And so that's good, right? That's what we wanted. So again, just re-simplify this to K. We have no numbers yet. And perfect, right? So now our rate law matches what we observed. And so note, right, the last step doesn't matter in the mechanism because, again, it's fast, so it's not part of the rate determining. And again, right, you can tell that from your mechanism that we were able to, again, right, derive that same rate observed. So again, this is too fast, not part of our rate law expression.
And how did you build it from N2O2 to
From N2O2. So that, right, all we care about is how is the concentration of this prior, right? So this was dependent upon the NO squared concentration. But then after this slow step, right, then we have this N2O intermediate, but this is kind of irrelevant since it's fast. Did that clarify what you're asking?
I'm still trying to get it.
Yeah, because remember, right, the N2O2 is your intermediate. Yeah, and then not only that, right, so then it does matter here. So, right, so it is part of this rate determining step. But then the question is, well, how do we get the concentration of N2O2, right? And then, so that's where we got that expression. that this concentration, right, is dependent upon this first step. And then, right, again, we have equilibrium. So if they're at equilibrium because it's fast, right, they're going at the same rate, which is how we got that expression and substituted it in. Does that kind of clarify? Because like, well, and maybe the other problem is because, right, you're not going to be determining all these steps on your own, right? You're going to be given out, here's kind of the proposed mechanism, and then it's just like you verify it, or you verify like what's the rate determining step. Because otherwise, right, you wouldn't really know that this is an intermediate, and you just kind of have to make more guesses based off of that. But that's kind of like beyond this course, right? We're just kind of saying, given these steps, can you break it down and show us, right, that this rate law, it matches, essentially.
Does it have anything to do with the slow rate? Just the H2 is the slow rate?
Yeah, well, the slow rate is this two reaction, right? The H2 and the N2O2 reacting, right? So whatever that is, you know, we don't know. Again, it probably something with the activation energy, something with the orientation, right? So that's the slow step for whatever reason. But then it goes back to, since that's the intermediate, we have to express it as a reactant. So let's try some more. When we do some more problems, let's see. So I forgot to put our reaction here. Maybe I put it. So here's our steps. Let me show you our overall reaction. So the overall reaction is 2 equivalents of ozone give us 3 equivalents of O2. And here is our proposed mechanism. So shown in 2 steps. So we have, right, our fast step and then our slow step. And so then we have to be given the rate law. And so then it says that our experimentally observed rate law is going to be equal to rate K times ozone squared over oxygen to the -1. And so then the question is, does this match? So try it for a few minutes. Kind of what do you have to do? How do you write the different rate laws, right, for each step? And then how do you express any intermediates as a reactant? So that's what we're, again, asking. All right, so kind of walk me through, what do we have to do? Mon, what'd you start off with?
I started off with isolating the low oxygen concentration in the first rate.
So, yeah, just, can you start us off with, what's your expression for this first step?
Yeah, K1 O3 concentration O3 equals K negative 1 concentration O2 concentration of oxygen.
Excellent. So this is, right, perfect. And you want to, again, you could just start off with even just that, right, for the first step. And then recognizing, again, fast equilibrium. So yes, they have to be equal to that. So that looks good. And so then where'd you go from there?
I divided each side by K negative 1 concentration O2. Leaving the lone oxygen concentration alone so that I could input it into our slow rate.
So this is sounding promising. All right, so then we're here, and then you said plug it into the slow rate, but let's write down what that is. So what do we get for our slow rate?
Do you want me to do that?
Let's just, anybody want to chime in? Lexi, did you get a slow rate? Jonathan, how's your slow rate going? What'd you get? So what happens in the second step then? Yeah, and so right, that's all we need to write for our second step is so K2 is dependent on that lone oxygen plus ozone, right? So that's all that we're saying here. And so now let's substitute though. So don't overthink, right, your rates. So it's just about what reactants are going on, right, in each little unimolecular, or not unimolecular, each little visual, right, mechanistic step. And so that's the whole point, is that it should cancel out if it's fast. And so then do the substitution. So, right, so again, I'll just rewrite it down here. So K2 is equal to our lone oxygen radical times ozone. So ozone, right, is part of our initial reactions. We said 2 equivalents of ozone gives us oxygen. So we just need a substitute for here. So now just rewriting, so then our rate law is dependent upon, so now we have, right, ozone squared times our O2, right, and then obviously K1, K negative 1, which we can get rid of. Sorry, I think I did something wrong. I just wanted to have K2. Sorry, K2 times this. So we're substituting, so yeah, K2 times this. And then, right, simplifies to K. And then yes, matches with our overall rate law that we were given. So right, it says experimentally observed was this of K ozone squared over oxygen. And yes, we verified that from our proposed mechanism. So then we can say, right, proposed mechanism works out. Does that make sense? Yeah.
Just one clarification. The K value in the overall reaction, will it match second, steps, K value, or is it kind of like the concept of like C can mean any number in like calculus?
Yeah, it can kind
Okay,
of
cool.
mean,
That's what I
yeah,
thought,
it's
yeah.
kind of archaic, but again, we need like data, so it would all work out, but we don't have any data either, so that doesn't help us.
Where you get, O2 on the bottom, is that why it's -1 because it's on the bottom?
Yeah. Yeah, because from our bottom, yeah, just rearranging. All right, that's probably a good time for a break. So again, just kind of review that math. If you have questions, just let me know. But yeah, let's take our 10-minute break. We'll come back at noon.
Marissa, experimentally, what does a negative rate have on the reaction? Like, what does that like? What does that mean for in terms of like O2's effect on the rates and the concentration?
It seems like as you make more, it's almost like negatively affecting the rate, like some sort of competition, but
Like, the higher concentration it is, the slower it gets because of that equilibrium.
yeah, because your mechanism just depends, like looking at the slow step of just that one. So yeah, but if you're creating O2 as well, then it implies some sort of competition mechanism.
I like this stuff. on my blackboard, it's showing up that my funnel is a 0. And I was wondering if you're able to maybe fix that so I can have a better sense of my grade.
Probably not, but
No worries.
I don't know why Blackboard has been doing that for random students. It like gives them a 0 on an assignment, and then I like try to delete it.
I've just been taking my my total score and then minusing
And you
the
gotta
105.
weight it properly. So
Yeah.
either way, your grade is probably not accurate.
Zeros, I have some for you.
Yeah, has everybody got a 0 on the final for some reason?
So,
It shouldn't be. I don't know. Your overall grade is inaccurate, so I shouldn't even show it.
whereas Marissa, one, I asked Marissa what the negative divided by,
I didn't get to the bottom.
yeah, so remember that this is an equilibrium, so it can go both ways. So if we imagine, let's put that in the sense of like collision theory of reactions, you essentially have what this is saying that ozone is going back and forth from like splitting off into O2 and a single oxygen and coming back together and splitting off and coming back together. So there's like this equilibrium going on of like that. So that means that we can equate these two rates. So the concentration of ozone in the atmosphere is equal to some is connected to the concentration of oxygen in a single like O2 and a single oxygen in the air. So we can, since these are equated, we can then, and I do this in my head, but essentially we can isolate the single oxygen because this is a intermediate group and we don't want it in the water right now. So we can create it like this by dividing A-1 and 2 over this, so just the concentration of oxygen would be significant. And then we can, now that this is, now that we know what this is equal to, we can input that.
So you just go in with the equation.
Exactly. And then we have this. Well, it's all algebra. And that's exactly what we were talking about, that's what the lecture was about. So then now that we have this, we're now trying to simplify this. So, have you taken calculus? So like
All right, so now I think we're ready to come back. Where y'all going? Oh, right. Okay. All right, have a good one. All right, let's look at our next bit. All right, so this is important and actually related to lab today. And so I think this was actually teased back in chapter 17. And so we kind of teased this of the effect of temperature. And I think back in chapter 17, right, we just gave some vague generalizations. But now we're actually going to quantify that. And it's actually pretty powerful. So we have our Arrhenius relationship here. And so we have our equation. So, right, whatever our rate is equal to A is going to be our frequency factor. So this is just going to end up being a constant. And A times e to the power of negative activation energy. So right, EA is going to be our activation energy over RT. So just note your units in that. So of course, activation energy is going to have to be in joules given this scenario. And then notice your gas constant. So again, we're in our joules gas constant. So joules per Kelvin per mole. And so that looks good here. So we'll be able to make our relationship or be able to figure out our activation energy, so kind of depending on our problem. And so again, just kind of visually going through what this means. So we have, right, our activation energy. So again, this is what's meant by, right, sufficient energy. If you want to go into the rabbit hole of like CHEM papers, so that's what like chemists are going to be looking into, right? Like literally looking at the exact orientation and trying to figure out what's the electron voltage, right, required for that transformation, and you can quantify that. And so again, just shown here, we just have our usual reaction energy diagram. Notice this is exothermic since our energy of our products is lower. So we've lost energy. And so then, right, just kind of explaining. So obviously there's an energy barrier. And so this could be, right, for different reasons. So obviously we have to go into some sort of activated form and also be able to perhaps make some sort of transition state. And so this is kind of differences in our vocabulary. So, right, our transition state, this is just, right, temporary, and it may not even really exist as like an isolatable compound. And so it's questionable whether you can see this or not. Again, it depends, very situation dependent, whether you can detect it or not. And then, right, again, our activated complex, part of why it's temporary and call this transition state is, right, it would be like the state where you're partially breaking and forming bonds. And so this is just an example of, again, what might create that energy profile. And so this is kind of interesting. So this is a phenomenon that can happen where this isonitrile can flip around. And so right now it's attached to our methane here, the nitrogen. That's actually not typical. So it wants to usually attach at the carbon. And so just showing us, right, the transformation of that. And so again, in this case, our transition state would be this intermediate state where we have kind of this weird temporary bond between our C and N as it does this kind of flip thing. And obviously, right, that's high energy, not really favorable. And then frequency would just kind of be related to rate, right? So turnover rate, how many molecules can be formed in a period of time. And so I'll again put like turnover, right? So this is again just another measure of how much product you're getting. And so that's something that, like, if you were to read some papers, it would discuss frequency or turnover rate, right? So that's what you're getting at if you're trying to make a cool new catalyst to save the world, right, for CO2 or N2 activation or whatever. So part of what makes a good catalyst is it would have to have at least comparable turnover rate to like nitrogenase or other natural catalysts. And so again, right, it's just telling you, obviously, again, high energy state, and it weakens our bond, so we can rotate it. And so then our Arrhenius factor just represents our fraction of reactant molecules with sufficient energy to make it over the barrier. And so other key points, so obviously increasing the temperature increases the kinetic energy. And so, right, again, we've talked about it in theory. So of course, right, increasing the temperature leads to an increase in kinetic energy, which is, of course, right, more productive collisions. And so again, right now we're actually kind of quantifying it, how we'll see this increase in temperature will increase, right, the number of molecules that are obviously going to react, and obviously will increase the reaction rate in a way we can, again, quantify. Blah, blah, blah. So this is just a good diagram to show us, right, our distribution. And so of course we have our energy profile here, and so notice, so T2 greater than T1. Remember our spread, right? So this is kind of related now to our speed of our molecules, but now overall, right, there's still more in our area under the curve that are moving faster. So again, that's why they're going to have more productive collisions. So these are just distributions. Oop. And then, so again, kind of where are we going with this? So I believe this is where you're going with this in lab today, if I remember correctly. And so this is one form, or another form of the equation, we should say. So we have our natural log of our K rate is equal to, right, our negative activation energy over R. And so R is going to be our gas constant, right, 8.314. T is going to be in Kelvin, of course, and then plus our natural log of A. And so obviously, right, there's going to be some graphs made at some point And so you're given this y equals mx plus b form. And so, right, this is your plus b for ln. And then we have our x is equal to our 1 over temperature. And so again, key points. So our graph of our natural log of our rate versus our time should give us a straight line. And then, right, so notice that we can, from our slope, get our activation energy. So just, right, multiplying it back out by the r. So that's all this is shown here, right, just getting that back out. And then the y-intercept, this is important, will be equal to, right, your natural log of a, so that will help you get that value. So this is one form of the equation. And then probably this one will be more useful. So this is, again, another form. So this is often used probably in word problems in class as well, or again, it may be appropriate for lab today. I don't remember. Actually, I think it is appropriate for lab today because we'll have some 2-point datas with our temperature. So again, right, we have our rate of K2 now over K1, and we can determine our either activation energy or again, whatever we're interested in from our 2-point data. So then that should give us activation energy. And then again, right, obviously 2 different temperature points. Oh, and then, sorry. Don't know how that. All right, so now let's look at our problem here. And so we're given nitrogen dioxide and carbon monoxide give us nitrogen monoxide and carbon dioxide. And so we're given our rate constant at 2 different points. So it says our rate constant at 207 Kelvin is measured at 2.54 inverse molarity inverse seconds. And then at 895 Kelvin, it's going to be 567 inverse molarity inverse seconds. So I'll just rewrite those. So 2.57 versus 567. And so see if you can find the activation energy. The gas constant, so in this case, the 8.314, the joules per mole Kelvin. Oh, sorry, EA is our activation energy, sorry, I didn't hear you.
But then on the A, negative EA over EYT.
So you want this one.
Oh, yeah, I know, I just.
Yeah, because we don't have A, right? So we can't use this form of the equation, so we have to use our 2-point form to find activation energy. So those are these that I gave you, right, the rates. So it looks like people are punching in. So I'll just kind of set up. And again, just kind of make sure that you keep, right, K2 consistent with T2. So you don't have any scrambling of variables. So then you can just set up, right, our natural log. I'll set this one to be our K2 conditions, right? It doesn't really matter who's who. The signs will work out. In the end, you just don't want to flip-flop. And so then 567 over 2.57 is equal to our activation energy over 8.314. Again, T1 conditions minus T2. Luckily, they gave it to us in Kelvin. So we didn't have to think too hard. And so right, not too bad for the setup. And then, so then it's just algebra, or plugging it in from there. Let me fire up my calculator. So again, just make sure all your buttons are functioning how you expect them to. So yeah, I'm just mathing. And then divide it by, let's see if I don't mess up this algebra. So then, let's see, we get 145,000 joules for activation energy, and I see thumbs up. Thank you. Appreciate that. 96 joules, right, again from our gas law constant here. And then it did mention it that it wanted it in kilojoules, so we can just shorten that to 145 kilojoules per mole there for our activation energy. So yeah, that's pretty typical for those problems.
So how did you get to the 145?
Oh, just the algebra, and then, right, did you get the 145,000 joules here?
I haven't continued on to that step. I was at the EA over 8.315.
Yeah, because that's just math, plugging it in, because that's what you get when you plug it in for the EA, and then that answer is in joules. So then just divide by, 1,000. Questions, other questions? So this will be pretty common, so you'll see that. All right, I think my notes were scrambled on this one. Yeah. That's where your practice problems were. All right, let's look at catalysts, or at least go over catalysts. And so catalysts are, of course, substances that affect a rate without being consumed. And so here's just one example of a catalyst. So going over this, again, ozone plus oxygen radical to create O2. So this is slow, but then catalyzed by some chlorine, then it is fast. That's one example. Obviously, there's all sorts of catalysts, from your catalytic car converter to our famous Grubbs catalyst, which look at, oh, there's our Grubbs catalyst. So these are just famous olefin metathesis catalysts, and there's like a bajillion of them. Again, just kind of show you, let's see if we can kind of try to find if it has a mechanism on Wikipedia, at least roughly. So yeah, no, that's a catalyst. I'll have to find a better mechanism, but basically, right, with our catalyst, it can form some sort of intermediate, right, where your substrate actually binds to your catalyst. Actually, no, that's not. I was trying to find an actual mechanism. But basically, right, it binds to your catalyst, and your catalyst spits it back out. So this is just showing the reaction. Unfortunately, it doesn't really show the mechanism in this paper. So again, right, this is your starting material. It binds with your catalyst, and then catalyst spits it back out to give you your products there.
Does it essentially like orient the molecule in a way that it makes those reactions easier to happen?
Yeah, I mean, that's a basic, oversimplification that it holds it in place, or like, with enzymes too, same sort of thing, kind of a lock and key thing, or it's holding it in place. But yeah, and then we won't get into like the metal chemistry of how it works, because it's just like oxidation reduction reactions where it adds it and spits it back out. And so again, right, they are not consumed. And then we should at least mention, so right, usually in chemistry, we're usually talking about positive catalysts because we're trying to force some reaction to occur. But in biology, you might talk about negative catalysts, which would be, right, some sort of inhibitor or something. So, or anything, right, that blocks biological pathways could be considered some sort of inhibitor. So again, kind of depending what you're talking about. And so an inhibitor obviously would just also bind to the active site and then make it slower and obviously create a barrier. And so the other important thing to understand is, yes, right, you're creating a whole different pathway for your reaction, kind of like I was trying to poorly show with the Grubbs catalyst, that, right, you have a new pathway, since again, right now it's going to do oxidative addition to your catalyst, and so that's a lot favorable. And then it's going to go through 2 steps. So, right, oxidative addition, reductive elimination for your Grubbs catalyst, 2 little steps with a lower barrier versus the olefin metathesis, which I don't know if it goes at all, honestly, uncatalyzed, but right, obviously, large transition state, difficult to overcome. And so this starts to get into kind of how you make a catalyst or design. So a homogeneous catalyst would be all species in the same phase. And so the Grubbs catalyst would be a good example of that, or many other like chemistry catalysts. And all that means is like it's usually something in solution, right? So you basically mix everything in. Kind of the problem with this homogeneous catalyst is that it's hard to recover though. And so that's where you get into like catalytic efficiency, because you would ideally just want 1% to maybe 10%, but 10% is honestly pretty high for a catalyst. Because again, you're assuming you're not going to be able to recover it if it's homogeneous. That's just generally how it goes in the workup phase. You're going to lose your catalyst. Heterogeneous catalyst, obviously, this has some industrial advantages. So notice, right, your species would be in a different phase. So again, think of like your car catalytic converter, right? So you pass gas over, I think it's platinum palladium that's used in the catalytic converter. And so obviously, right, that catalytic converter is easy to separate from the gas phase. Separate to, you know, by some thieves who want your catalytic converter. But, right, again, the whole point is recovery is easy. And so those are different things to think about if you were to go on, and probably this is more towards the chemical engineering side. Could get into the research of it, but again, these are kind of two different veins of research. Whether you go heterogeneous, and usually this is more like surface materials chemistry, which is honestly outside of my personal interests. I'm more of a homogeneous catalyst person, not that it really matters. Anyways. Blah, blah, blah. So again, we said they speed up the reaction. And, right, our catalysts, like we mentioned, hold our reaction in some sort of orientation or do some sort of mechanism. Again, kind of oversimplification. Usually, yes, they're going to, right, break some bonds. So again, that's what that Grubbs catalyst does, is it makes it easy to break those bonds. And yeah, our homogeneous reactions, again, form a more stable compound, or sorry, form our activated complex. So again, just thinking about some sort of intermediate where it's bound. All right. And again, just illustrations, right? Homogeneous, all same phase, so it could be gas, generally solution in chemistry. And then heterogeneous, right? This could be gas and solid or liquid solid. And again, just kind of showing how it's going to absorb on the surface for, again, especially these heterogeneous catalysts. And our reactants absorb, and then, right, then they come react, and then deabsorb. And so then, oh, this is somewhat related to our lab then. Let's see, might go through the derivation for your last week's lab. And so, right, we have our, of course, our biological catalyst. So we looked at urease in our lab last week. And so obviously, many of our molecules are large and complex. So we have to have catalysts, right, to break it down. There's amylase, right, to start breaking down carbohydrates, all sorts of enzymes, right, to break down everything. And so we kind of saw this in our lab. So again, we kind of will work towards breaking down our rate law expressions. But we can kind of think back to, right, the urease and what it was trying to do. And so basically this is what we were doing, right? We had our enzyme, so urease, right? We had our urea. And so that was, sorry. So that's what the first step of the lab was talking about. That it's like, okay, you have some sort of enzyme substrate, they're going to bind, and then, again, I think your lab mentioned that this is generally the fast step, which we looked at. And then, right, once it bound, the enzyme substrate, and then what you were observing, right, was your product formation. Sorry. I got sick over the weekend, and now my throat's just like drying up randomly. I hate that sensation. Okay. And so, again, now we're kind of thinking about, well, that's what happened. So enzyme substrate, and then again, product, right, which we looked at with our color change. Back from our lab. And so then, let me actually pull up last week's lab. All right, so that's essentially what we did, right? And so this is now our lecture, right, what I was saying. Okay, so that's just what we reviewed right now, right? So again, fast step. So ES, enzyme substrate, and then our K2 here, enzyme plus product. So that's where we are now in chapter 18. And so now it's basically kind of showing us the same steps. And so why we care about this is it is in the back. Oh, is it not? Maybe I lied. Maybe it's in this week's lab, the derivation. And now I can't find it. I'm looking for. Is it your homework? Oh, jeez. No, I'm not crazy. I just don't know where it was. Because somewhere you're asked to do a derivation, but maybe it's your homework. Does your homework look like it? All right. I look like I'm insane. We've done this every year. I just like literally cannot find what assignment it's in, and now I'm pretty upset. Oh, I give up on life. Come on. I thought it was on last week's lab. I am so tripping. Sorry, I was trying to pull up a homework. It's not in your chapter 17 homework either. All right, well, boy. That was strange. Because somewhere I thought you had to solve for the steady state approximation. but I like literally can't find it now. I don't know. I might have to get back to that and show you where it was. Otherwise, we could do the derivation. I just wish I could find the assignment that it was from. It's a little annoying. All right, let's see. I'm still trying to figure out where that ES thing was. I have no clue. All right, maybe let's skip. Okay, I'm going to skip this for now because I want to figure out where the heck it is and what assignment. I don't know what's going on. Since, like I said, we've literally done it every year, so now I have no idea why I can't find it. All right, let's look at your homework. Let's shift. All right, so I have your Chapter 18 homework. And so let's just try the first one. So a little warm up. So we have our first order reaction has a rate constant of 1.4 times 10 to the negative 7 inverse seconds. So calculate the time required. If our initial conditions are 0.175 molarity, how long will it take to reach 0.1 molarity? So you might have to look at Chapter 17. So how do we do on A? So what do we do for A here? Yeah, Mon, you want to go for it?
Since it's a first order reaction, and we start to create the rate law, which is the natural log of desired A over initial A concentration equals the negative KT.
Oh. All right, sorry, one more time. What was the equation?
A desired over A initial natural log of that equals negative KT.
So ln of A initial over A at T is equal to,
It's the other way around.
oh. So A at time
A at time.
over A naught is equal to negative KT.
Correct.
I think you could flip it and have KT, but either way. And then, so plug in, oh my gosh, sorry. Move back up. So then plug in. And so then A, so negative KT. Oh, we're trying to solve for T, giving K. Oh, I should put T here. Make that clear. Divided by negative. Oh, that doesn't seem right. What did I do? Oh, because I didn't do that right. Sorry. Divided by. Sorry, I messed up my sign. That should be positive. And so let's see where we at. 1, 2, 3, 4, 5, 6. So about 4 times 10 to the 6 seconds there from the calculator.
I got that as well.
Excellent. Other questions? All right, let's skip down. So I think that was a good warm-up, but a lot of this, or at least 2, should also be more chapter 17. Let's try to look at some of these reaction mechanisms, because these are a little trickier. So let's just start off with 4 here. So it says, so HCl reacts with propene, and there's our formula for propene, in the gas phase according to this reaction. And then, so notice, right, we're given our measured rate law. And then which, if any of these mechanisms are consistent with our observed rate law. So how do we go through that? So kind of take some time, right, try to analyze it. So what are we thinking?
I think it's B because in the slow step, they're both intermediaries and the products for those intermediaries are their 3 HCl, CH3, CH2.
So I like it. And so we can kind of go through, so there's different ways to kind of reach this conclusion of B. So what I'd probably do is kind of first start looking at A. So what's wrong with A when you look at the mechanism there? Remember, right, you can always write things and express things. But what's your slow step? Kind of dependent on, yeah.
The slow step is dependent on CH3, CH2, and hydrogen, so that would mean it would be dependent on those.
Yeah, and like part of the problem is, right, so we only have 2 HCl's here, and then this says HCl3. So that's where, again, kind of B at least stood out, you know, without going through any more detailed calculations. You're just kind of looking fast, HCl, HCl. So that looks good. And then, of course, write your propene rate. And then, right, again, you could figure out what's wrong with C. So again, C, you are missing the 3 HCl's is kind of the big hint, in my opinion, for this one, where you can determine that. So that's good. questions on that one, or does that kind of make sense? All right, I think we're out of time, actually. So probably on Thursday, we'll do more practicing. I'll try to figure out the steady state thing and where that problem went. And we can at least go over it, if nothing else. And then we'll look more at your homework, do some more practice problems. And we should be in good shape. All right, I'll see y'all in lab. Should be a fun lab, more measuring rates and all that. And then, of course, quiz Thursday. We'll be over chapter 17, so we'll be back to our quizzes. All right, have a good day. I'll see y'all in lab.